Good afternoon. My name is Vella. This is my study what I'm doing with University of Malta, and together with my co-tutors Jason Gauti and Alexei Dingley. So basically, I will talk about why the study was needed, some related work that has already been done, my methodology, the results, and my final conclusion and future work. Also, I thank OpenSky because with their help, giving us access to this database, this research could happen. So, brief introduction, we know that traffic is getting up between 10 and 20% increase in flights when compared to 2019. In June 2023, there was an average of 32,000 flights. In 2024, that increased by 5.2%. One of the main delays is also to weather. In June 2023, there was about 1.3 million minutes in delay. That increased by a heavy percentage of 53.8%. Currently, Eurocontrol is working with to decrease these delays, where 12 million miles less flown. In result, there was a reduction of 240 tons of less of CO2 emissions. So the key priorities to decrease this delay mainly are from ground people on the ground, flight planning, air traffic controllers who take their responsible TMA, and also the pilot who's in the flight deck and monitoring the flights. So currently there are two types of delay methods when it arises. One of them is point merge. It is also close to tromboning, and it's mainly used by 44 airports in 20 countries in about 4 continents. And then there are the longer delays that are made in a holding pattern stack. As one can see on the right, where the plane is runs in a race course manner until it's time for it to land. So for our study, we decided to use London Heathrow. As was found from before and from previous studies in Europe, 36% of arrivals at Heathrow spend time in a holding stack. It's quite a challenging airport because it's one of the busiest. It has only 2 runways, 5 terminals. To go for Terminal 4, you have to cross a runway that may be at the landing runway or the departing runway. Also, it has 4 holding patterns, as we can see on the left. 3 of them are right-hand holding patterns, and one of them, Lemberg, is the left-hand holding pattern. So some related work, it was quite difficult to find about holding patterns to predict how long the holding pattern would be. But there was a study that was in Changi in Singapore airport, where they made a prediction about 500 nautical miles from the airport, where they did a delay prediction. There was a speed adjustment by lowering their speed, then the delay would absorb at the cruise phase, and then the holding pattern would be abolished because there was no need for it. Like that, it helps also the passengers on board, since they don't need to go in circles. It would be more efficient since holding patterns happen at a lower altitude. The efficiency of the plane is much lower, so more burnt fuel. Also, holding patterns create noise to the people on the ground living near the airport. Also, it helps air traffic controllers since they have less cluster of planes in their space. So, on the other hand, there was many studies made for prediction of estimate of time of arrival. Many of them were like these machine learning different methodologies. And from all of these, all pointed that granted boosted trees were the main ones that gave the best array metrics. For our data acquisition, so we use OpenSky. We capture data, so we can see on the left in the box from April to August 2023, and we were capable to capture about 78,955 arrivals at Heathrow. And where you can see a heat map of all the arrivals at Heathrow. Upper right, where we have a sample of the data, we have the 4 holding stacks, and then the next step was, once we had the data, is to calculate the holding pattern, the length of the holding pattern in the stack. So basically, when a turn in the direction of the holding pattern of 20 degrees or more is detected, starter would start, and then if opposite direction of 5 degrees, the starter will stop. The timer will stop, and the difference between the timer would be how much the plane had been in the holding pattern. In case there won't be opposite direction, the timer stops when the plane gets out of the stack. So before that, the data was filtered for each holding stack. Also, the data was downloaded in a 30 seconds timestamp, so it was more easy for us to work with all that data points. So we use OpenSky through the traffic API via Python and Panda and NumPy data frames. We also downloaded the meter weathers from the Metaset on database, and we enter those in the Eurocontrol at map weather algorithm, where it gives you a score between 0 to 5 for some parameters for others between 0 to 30. The higher the number, the worse is the weather at Heathrow. This included freezing temperatures, wind, precipitation, phenomena, and even the cloud ceiling and visibility. A new function that we also found was the delay index. Is quite a new parameter, and this was not found in the past works. Basically, it gives you a score between 0 and 5. The higher the number, the more delay is at the airport. It's also divided as the arrival and departure delay index. That was taken from the radar API. Also, using the OpenSky, we took the type code of the plane from its own database, and then we entered it in the cargo document to know the work turbulence category and even the engine type. So basically, this is the total number of flights that we had at Heathrow from April to August. Biggins was the least holding stack that was used. Auckland was the second one. From April to June, Bovingdon was the most used, and then Lemberg was used mostly in July and August. And also, this is affected in the end in the results when we're testing the machine learning, as now we will see. So in the end, we had two types of data sets. So the phase data set, it focused mostly on for individual flights. So we had information for each flight, like the total holding time of each flight, the stack identifier, the work turbulence, engine time, ground speed, track, its attitude. We had also the weather score from the map, the number of holding flights that there were at the same time, the landing runway identifier, the landing crosswind, the headwind, a number of landings in the last hour, the departure and the arrival delay index, and the guiding time were the day of the week and the time of the day. Also, each dataset was calculated 3 times at the London TMA, 30 minutes before the TMA, and 60 minutes before the TMA. On the other hand, dataset 2 focused mostly on E-stack, so on the airport of E-stack. So we had 4 different datasets for dataset 2 for E-stack, where the average holding time, the number of aircraft in the holding stack, the minimum and maximum holding time, the number of aircraft for each work turbulence, the number of aircraft for each engine type. And also we found that some planes did not fly over the stack and given vectors directly to the landing runway. Also, regarding airport conditions, we calculated the number of landings in the last hour, the number of landings per runway during that time interval, the weather score from the map, the landing crosswind and headwind component, the departure delay index, and the arrival delay index. And the guiding time also took the day of the week and the start of the 15 minutes interval. So this is what it was more, this database was more focused on time, having a 15-minute time interval for each stack. So for the data set 1, we mainly used it for a regression problem, where we created 4 models, model 1 at the TMA, model 2 at the TMA minus 30 seconds, model 3 it was at TMA minus 60 minutes, and for model 4 we took all the data for model 1, 2, and 3, and we did it in a single data set. For the data set 2, we more seen it as a time series forecasting problem, where we created each model for each stack at Heathrow. So for our programs, we decided to go for light GPM and KLS for LSTM. Light GPM is quite great in boosting. We found that in the past work, it worked great. And also light GPM was created by Microsoft. It is easy to use. It is and handle a lot of light data sets. And also it leaves less memory than other programs to run. For KLS, the LSTM, it's a neural network, but LSTM focuses more on time series forecasting. It abolishes the problem of having gradient, the missing gradient problem, and also when having a large data set and having the ReLU activation function equation, the traditional neural networks can handle that. LSTM was modified to have better LI metrics. So for the regression problem like GPM, we'll use the grid charts cross validation for our hyperparameters, and we use with the help of scikit-learn. When we apply to LSTM, we use the min-max scaler to scale the data between 0 and 1 because it helps better the program. To process it, we use a 5 steps input. We use the classic stacked LSTM, so we had 2 layers of LSTM, where the output of the first one was used as this input of the second one. Like that, the program the machine learning can learn more about behavior changes in the data. Each layer had 15 neurons having the ReLU activation function, and the dropout mechanism was made of 20%, where 20% of the inputs were set as zeros, so that the machine learning wouldn't be too dependent on the data that we gave him. Also, an early stopping mechanism was implemented, where it feels that after a number of epochs, the change in the error metrics are too small, the program automatically stops. So this is the hyperparameters we use for using light GPM. We use the num-leaves, learning rate, the estimators, and the feature fraction, backing fraction, and backing frequency. Mainly, we went to input these grid chase parameters, and automatically using the grid chase cross validation, it's found which parameters works best with all these different kinds of combinations. Mainly, this exercise is done so the data won't be too dependent on the given data, and you don't have that outliers. For forecasting, we use the same like GPM and KLS, and we compare them. So for forecasting, we use window length. So for the training and the testing data as inputs, we use not only a single data point, but the previous number of data points, and that is called the window length. For like GPM, regarding the number of window length, we use the forecasting grid chase from sklearn API. And for LSTM, we use the grid chase cross validation. We set as a constant of 30, window length of 30 data points, which equals to 7.5 hours. And we use the max scaler as before, and we use the normal classic stacked LSTM and the 15 neurons with the ReLU activation function. For grid chase for LSTM, we use the batch size, the number of epochs, and the optimizer algorithm. So we got the regression, we got the results for every model for 1, 2, 3, and 4. We have the top one, we have the light GPM, for the bottom we have the LSTM. Overall, light GPM gave the best results with a root mean square error of 1.97 and mean absolute error of 1.27. We got higher with the regression model. We also can see that when the plane was much further from the TMA, the error metrics came higher. So once the plane was near the TMA, it had more accurate prediction of the holding time. Also, light GPM is capable of doing importance feature. So it gives you what features affected mostly the array metric. In case of LSTM, it's much more difficult since the neural network is difficult to have post-processing results. So we use it as permutation, feature importance, where it trains again the model, removing each time one of the features. And how much the array metric changes, it gives you what's feature has the most important that affects the results. For model 1 the TMA, we had the number of holding flights from both models. From 30 minutes before, for like Japan, we had the number of holding flights. At LSTM was the landing conveyor identifier. Model 3 had the same for both the time of the day, and when we did the aggregation of all models, the greatest important feature was the number of holding flights at the TMA. So from the table, you can easily see that the number of holding flights had the greatest effect on the holding time prediction. For the forecasting model, we can see that the light GPM had much higher root mean square error and mean absolute error. LSTM worked better with those. So basically, in this also we can see that for Bovingdon, both models had the highest root mean square error and mean absolute error. Mainly, this was since in August, when we tested the data, there were less flights in Bovingdon when compared to the other, and that could skew the data. Some methods we can use so this doesn't happen is implementing a smooth algorithms that creates fictitious data points to balance the data out. Also, we are using the LSTM. This is for every stack. We have the original data, the predicted data, and also the program is capable to forecast the data without giving it its input. We can say for low between 0 to 5 minutes of holding time, it predicted quite closely. When it has some outliers of high holding pattern time, we can see that in many cases it predicted there was going to be high holding time, but it did predicted exactly. So some conclusions, the regressive model, the light GPM worked better than the LSTM, having a root mean square error and mean absolute error of 1.97 and 1.27 respectively, and the time series LSTM worked better using the root mean square error and having a mean absolute error of 2.05 and 1.23. As seeing all this data, the regression model can help a lot the pilot since it's user data sets and inputs of each flight, while the time series can help, on the other hand, the air traffic controller mostly because it has information on every stack, and even can help the pilot because on the way to the airport, it can have an updated value every 15 minutes, how much is the predicted holding time at that time. Some future works to abolish the problem that we had before. We are trying to have a larger training data set, so it would be more balanced. Other parameters to improve model performance, for example, weather at other airports, where, for example, for the airport capacity, but it was difficult to get it online. Also, we are seeing, for example, the star removal price, which one have chosen the other, how that could change the results. As for the set, improving the current model, like using the smooth algorithm to have a balanced more data, and also exploration after machine learning techniques to predict aircraft holding times using the same data sets that we already have. Thank you all for your attention.
Thank you for your presentation, and we are ready for the questions. Online, everything is nice and clear. So can I ask you maybe, so Xavier just presented the part for the same airport, actually. So are you planning to use his research?
You can use it since we have the data set to maybe more see how accurate is the classifier that he did with this one.
For validation purposes.
Because the holding time was made manually and the data was validated by seeing the data, and it made sense.
And in your case, it's a bit easier because you know the points for holding patterns a little bit different.
I had the latitude and longitude of the holding pattern of Heathrow.
Great, and I think OpenSky provides a perfect platform because we have all the open codes and you can compare the results and reuse